Hi, everybody. We're going to start talking about Chapter 8. In the way that I organize the class, we do things a little bit out of order relative to the textbook. We do Chapter 9 first, and then we do Chapter 8. I like it better that way. But the beauty of online teaching is that if you don't like it that way, you can turn it around. So Chapter 8 is about acids and bases and how they have different properties that can affect their partitioning and fate in the environment. Hopefully you remember something about acid-base reactions from your general chemistry classes. Some organic chemicals have exchangeable protons, meaning they can lose a proton. Those are acids. And some have lone pair electrons which can accept a hydrogen. Those are bases. And the ionized form of these compounds, the one that has either lost a proton to become an anion or gained a proton to become a cation, the ionized form acts very differently from the neutral form. It's going to have a different Henry's law constant, a different KOW, etc. And these proton transfer reactions where a chemical loses or gains a proton, are very fast and reversible because we're talking about water as our medium, and we know that there's lots and lots of protons available in the water. So there's always a proton available. So these reactions are fast and reversible, and we can treat them as though they're at equilibrium. So this makes a nice bridge between the first half of the class when everything was at equilibrium and the second half of the class where everything is not at equilibrium and we have to deal with rate constants. So acid-base reactions sort of fall in the middle. They're still a chemical reaction, but we can treat them as though they're at equilibrium. So, for organic acids, hopefully, again, some of this is familiar to you. We have our acid, which we'll call A, and it's got a proton stuck to it, which we call H, so that's HA. Add a water molecule. The water molecule can steal away the proton to become hydronium and leave you with a minus, a negatively charged anion. And since we know that at the pure water is our reference state, and by definition, the delta G of this reaction is 0, and the equilibrium constant is 1, then we can write this equation in a slightly different form and just write it like this. HA loses a proton to become A minus, and we just sort of ignore the fact that a water molecule is involved, even though we know it is, but we're just going to ignore that and write it this way. So the equilibrium constant for this reaction is Ka, the acidity constant, and we know that natural log of any equilibrium constant is equal to minus delta G of the reaction divided by RT. So that much, hopefully we remember from general chemistry. So at equilibrium, we have products over reactants, and normally we would just write, here's the products, H plus and A minus, and here's the reactant, HA. But because we're in aqueous solution and we're dealing with ions, we also have to deal with the activity coefficients here. So those are added here. So really, if you take the whole thing here in these brackets, this would be the activity of HA in the solution. So this Ka, the equilibrium constant for this acid dissociation, is called the acid dissociation constant. And you typically measure it in terms of the activity of the protons, so that's this. But then here you don't really worry about the activity coefficients for the A minus and the HA. And the reason for that is because you typically measure the activity of protons by sticking a pH electrode into the system. And a pH electrode measures activity. It does not measure concentration. Whereas on the flip side, you measure the actual concentration of A minus and HA because you're measuring those as chemical contaminants, maybe by HPLC or something, and there you're measuring the actual concentration, not the activity. So when you're doing that, what you're actually doing is measuring what's called a mixed acidity constant, because the protons are in terms of activity, but the HA and the A minus are in terms of concentration. So the activity coefficient, the equilibrium constant, Ka, is a mixed acidity constant. If you're at low ionic strength, you can assume that all those activity coefficients are pretty close to 1 anyway. You can just get away with writing the equation this way, where you're just writing it in terms of concentration and not worrying about activities. So if we write it this way, we could rearrange it a little bit, take the log of both sides. So log of A minus over HA is equal to the log of the equilibrium constant plus the pH. And so when just in the same way that pH is equal to negative log of the proton concentration, pKa is equal to the negative log Ka. And so then this ratio here is equal to pH minus pKa, which means that you can pretty quickly determine how much of your chemical is in the A- form and how much of it is in the HA form by knowing the pH and knowing the pKa of the reaction. And so if you look at this for a moment and let your mind figure it out, then you know that when pH is equal to pKa, this whole thing is 0. 10 to the 0 is 1. And so this ratio here is 1. And this ratio is 1 when HA is equal to A minus. So they're equal in concentration when the pH is equal to the pKa value. For organic bases, the treatment is similar, except that you have B picking up a proton and leaving behind an OH minus hydroxide. And you could write a Kb, a base constant, a base dissociation or association constant. But that gets a little confusing, so what we do instead is we just write it as though it was an acidity constant. BH plus on this side goes to B and H plus over here. And then we could write this in the form of a Ka. This is in the form of an acidity constant. So we use the whole idea of pKa regardless of whether we're talking about acids or bases, okay? So for the acids, when pH is equal to pKa, then the H minus and the HA are equal in concentration. For bases, when pH is equal to pKa, then BH plus is equal to B in concentration. So what kinds of chemicals are we talking about? Well, in the red here we have things that act as acids in the environment, and in blue we have things that act as bases. And you'll notice that most of the things that act as acids over here have oxygen in them. Okay, so for example, here's a carboxylic acid group attached to a benzene ring. That's called a benzoic acid. Put 2 nitro groups on it, you got yourself a 2,6-dinitrobenzoic acid here. And so this proton right here is the one that can get lost, and this chemical can, become negatively charged. Instead of a carboxylic acid, it's a carbonate. I don't know what it is. Benzoate, excuse me. Benzoic acid, benzoate. So yeah, all of these are, hydroxide groups, carboxylic acid groups. Those are the ones that act as good acids in the environment. So here we have lots of carboxylic acid groups. The other thing that acts as a good acid in the environment is phenols. That's an OH group attached to a benzene ring. And you can see, so here's your plain old garden variety phenol. The pKa value here, pKa, is 9.9. If I add a nitro group to it, the pKa goes down to 7.2. I add 3 nitro groups to it, and the pKa goes all the way down to 0.38. Add a bunch of chlorines, the pKa goes down to 4.75. Add some methyl groups, and the pKa actually goes up to 10.9. So the phenol has its basic, pKa value, but then you can adjust that based on the addition of different substituents on the ring. Same thing going on up here. Here's your basic benzoic acid. It's got a pKa of 4.19. If I add a nitro group, I drag the pKa down to 3.44. 2 nitro groups, I'm down to 1.14. By the same token, here's acetic acid, 4.75. But if I add 3 fluorines onto that acetic acid, I drag the pKa down to 0.4. And then there's a few other functional groups that can act as acids in the environment, and they typically involve sulfur. So here's a thiophenol. There's the thio group, and this is the phenol part, right? And it's got a pKa of 6.5. Here's a sulfonic acid right here, pKa of 0.7. Here's another naphthene sulfonic acid, pKa of 0.57. Plain old ethane thiol has a pKa of around 10, 10.5. And your garden variety everyday aliphatic alcohol has a pKa value in excess of 14, which is another way of saying that this proton is not going anywhere. Okay, that proton is not exchangeable. As far as we're concerned, aliphatic alcohols do not act as acids in the real world because the pH never gets above 14. And then over here on this side of the slide, we're dealing with bases, and you notice they all have nitrogen in them. So anytime you see a compound that contains nitrogen, your first thought might be, well, that could be a base. So here's your basic aniline, got a pKa of 4.63. Add a chlorine, you drag the pKa down to 3.99. Add a nitro group, you drag the pKa down to 1. So here's trimethylamine. 3 methyl groups attached to a nitrogen, pKa 9.81, hexylamine, and then here's piperidine. These are all chemicals that have nitrogen in them. Nitrogen's always got its lone pair electrons, and they can attract a proton. And the pKa, of course, varies depending on the structure. Then you've got heterocycles. So these are cyclic structures, so carbon cycles, except that there's a heteroatom. Instead of just being 6 carbons in a benzene ring, nitrogen is here serving as the heteroatom, and that nitrogen can pick up a proton. You can see if you just have plain old pyridine, the pKa is 5.25. You add a nitro group on it, you drag the pKa all the way down to 1.23. Add a chlorine, you drag it down to 3.83. If you add some of these organic functional groups, some R groups, you can actually slightly raise the pKa a little bit. So anytime you see an amine, especially if it's attached to a benzene ring, or if you see a heterocycle, like pyridine, as soon as you see that, you should immediately think, maybe that could be acting as a base and picking up a proton and becoming positively charged. So just to recap, important functional groups, alcohols by themselves, not really important acids because their pKa's are too high, but carboxylic acids are important, phenols are important, and benzoic acids are important acids, organic acids. And then for bases, you got your good old ammonia here. This would be a primary amine. Here would be a secondary amine because you got 2 methyl groups attached to it. That makes it secondary. Tertiary amine has 3 methyl groups attached to it. You can see how the pKa goes down when you go from primary to secondary to tertiary. Well, actually, it doesn't go down uniformly, but hovers around 10.5 to 9.25. And then there's your aniline and pyridines. So whenever you see those types of functional groups, you have to stop yourself and say, that could be an acid or that could be a base. And I guarantee you that on the final exam, I will give you a bunch of chemical structures and I will ask you which of these are acids and which of these are bases. And you're going to have to be able to look at the structures and figure it out for yourself. So as with all the other equilibrium constants we've talked about in this class, we want to quantify the effect of temperature. When chemical reactions are fast and reversible, that means that their as you say in your country, their activation energy is relatively small. And if activation energy is small, then the overall delta H of the reaction also must be pretty small. So as with any other equilibrium constant, we can use an equation of this form to describe how the equilibrium constant changes as a function of temperature, and it has this delta H term in it. But for acids and bases, that delta H term is going to be pretty small. So these don't tend to be really huge functions of temperature. The pKa values of these chemicals are not very dependent on pH. And then the question always comes up, does the presence of these organic acids or bases affect the pH of the water that we're dealing with? And the answer is usually not, because we're talking about low concentrations of things that are serving as contaminants. We're not talking about huge, huge concentrations. And natural waters are almost always buffered by carbonate. If they have any exposure to the air at all, they're able to suck up carbonate. So even in relatively clean natural water, the carbonate concentration is going to be somewhere around 10 to the minus third molar. So as long as you have a neutral pH, then the addition of a small amount of one of these acids, like 10 to the minus 5 molar, is not going to make any difference to the pH. So where this becomes important is where you have really, really high concentrations of these chemicals. You might have that in an industrial wastewater. So if you go to a wastewater treatment plant that treats industrial waste, one of the first things that they will do is test and adjust the pH to try to bring it to something neutral. Because if they add this high concentration waste with a very odd pH, either very high or very low, to their aeration tanks, they're going to kill all their bacteria because the bacteria can't survive that change of pH. So the first thing that they typically do is adjust the pH on industrial waste. So we could write an equation for the fraction of our chemical that is in the neutral form, and we're going to call that alpha. So that's the amount that is in the HA form divided by the total amount that's in the HA plus the A minus form. And we could rewrite that like this, and I don't know if you remember this ratio here, but we already said that ratio, log of that ratio, was pH minus pKa. So alpha is 1 over 1 plus 10 to the power of pH minus pKa. So if pH and pKa are equal, this is 0, 10 to the 0 is 1, 1 over 1 plus 1 is 1 over 2, it's 50%. So that means that 50% is in the neutral form, and therefore 50% is in the charged form. So this works great if you're an acid. If you're a base, then the fraction that's in the neutral form is 1 minus alpha. So you just calculate alpha and then subtract it from 1. So the chemical structure determines its pKa value. And because we're dealing in the real world, we're mostly concerned with compounds for which the pKa values are somewhere between maybe 3 and 11. Because in the real world, it's rare that we get to a pH below 3, and also rare that we find a place with a pH above 11. So these, again, would include the aliphatic and aromatic carboxyl groups, hydroxyl groups, phenols, aromatic hydroxyl groups, not aliphatic hydroxyl groups, but aromatic hydroxyl groups, which are phenols, aliphatic and aromatic amino groups, nitrogen heterocycles, and some thiols. And these classes of compounds have pKa's which vary widely across that pH range. And so here's an example. This is where they've attempted to look at the difference between the pKa of the chemical they're interested in and the pKa of the same chemical, except instead of with some weird substituent on it, it just has a hydrogen. And so that has been related to the what are called the Hammett constants, which we're going to talk about in a minute. But the point here is that these differences in the pKa, so this is a difference of 1 pH unit, and you can see that there's lots of chemicals that fall along these lines where the pKa can change over 4 orders of magnitude on this plot. And you also notice that there's some linearity. If you put the phenols here, they all fall on a line. Benzoic acids all fall on a line. And so you can start to make some models that describe the behavior of chemicals and how adding substituents onto this aromatic ring here might change the pKa of the compound. Why does this happen? Well, if you cast your mind back to your organic chemistry class, you remember that we have a couple of different kinds of effects that are going on when we have aromatic rings. We have inductive effects, which are either positive, which are electron donating, or negative, electron withdrawing, and they either push or pull electrons, right? So electron donating groups include O minus, NH minus, and alkyl groups. All kinds of organic side chains will tend to push electron density and be electron donating. Most of the substituents that are of interest to us as organic chemists, as environmental organic chemists, tend to be electron withdrawing, so that's all these NO2 groups, all of the halogens, fluorine, chlorine, bromine, iodine, ethers, phenyl groups, these are all electron withdrawing groups. So that takes care of the inductive effects. And then the other thing you remember is that when you're dealing with aromatic rings, you have resonance, and so you can have delocalization effects. This is the extent to which the electrons in the ring get delocalized and moved out among the other substituents. And so these delocalization effects are positive for halogens, amino groups, phenols, and OR ether type groups. And they're negative for NO2 and some others. And then there's these weird-ass proximity effects, which are very difficult to predict. They might be things like intermolecular hydrogen bonding. I'll give you an example of that. And then also steric effects can affect the size of the molecule. It might have the size of the substituent might have an effect just because it's so large it gets in the way and prevents certain reactions from happening. So for example, here's your acetic acid. If you add an extra methyl group on the end, you have propanoic acid. Add another methyl, you get butyric acid. And so adding those methyl groups, your pKa goes up slightly, 4.75 up to 4.87, and then really not much change for another methyl group to 4.85. So these alkyl groups are weakly electron donating. But if we start to add chlorines, if we add the chlorine all the way down at the end of the molecule, at the end of the butyric acid, the pKa goes from 4.75 to 4.52. So it goes down a little bit, not a ton. If we instead add that chlorine closer, one carbon closer to the scene of the action, we go from 4.75 to 4.05. Now we're having a bigger effect. And if we move that chlorine even closer, so that it's right next to the carboxylic acid functional group, our pKa goes down by almost 2 orders of magnitude, from 4.75 to 2.86. So the chlorines have a really strong electron withdrawing effect, but their proximity is really important. If they're not close to the scene of the crime, then they don't have much of an impact. So that's an example of inductive effects with methyl groups pushing and chlorines withdrawing. And then delocalization effects. So for example, for chlorinated phenols, here's phenol by itself, pKa about 9.9. And then if you start to add chlorines, you can generally reduce the pKa until you get all the way down to pentachlorophenol, where the pKa is down to 4.83. And then depending on what positions those chlorines are in, they can have a bigger effect. So 2-chlorophenol, the chlorine is much closer to the phenol group and has a bigger impact. So it lowers the pKa more than it would if the chlorine was in the 3 position. And the chlorine in the 4 position has even less of an effect. So there's a general reduction in the pKa due to the fact that there is a chlorine there that is caused by electron withdrawing effects. But then there's also sort of a specific type of reduction in the pKa that depends on the chlorine's position. So the 2,4,6 trichlorophenol has a much lower pKa than the 2,4,5 because the 2,4,6 has the ability to, has that resonance and therefore delocalization effect much more than the 2,4,5 does. So here's an example. You might remember from organic chemistry that the more resonance structures that you can draw, the better the impact, the more stable the chemical is going to be, right? So if I just have a regular old methyl alcohol and I take the proton off and I get methylate, that's not very favorable because I can't draw any resonance structures here at all, and the pKa is really huge at like 16, so that doesn't happen under normal circumstances. But for phenol, the addition of this benzene ring lowers the pKa by about 6 orders of magnitude, just that one ring. So when I take the proton off, I have 1, 2, 3, 4 different resonance structures I can draw for the phenolate anion. And that's how I know that it is much more stable than just the methoxylate anion here. Same is true here. So here's a primary amine, methylamine, could pick up a proton, and you can draw lots of resonance structures for the unsubstituted or unionized aniline here. So if we have a phenyl group instead of the methyl group, we have resonance, and we can draw 1, 2, 3, 4 resonance structures, and so we know that this thing is much more stable than this thing because of the resonance, and as a result the pKa goes from 10.7 all the way down to 4.63. Resonance effects are heavily influenced by position. This is what I was talking about when you were doing your organic chemistry class. You probably talked about this, how ortho and para are in good position to do a lot of resonance. So here's para-nitrophenol. I can draw 5 different resonance structures here for the paranitrophenolate anion. But if I have my nitro group in the methyl position, the meta position, then I can only draw 4 resonance structures, and so this is less favorable. So because this is more favorable, it has a lower pKa, 7.15. This is a little higher at 7.28. Even though the nitro group is now closer to the scene of the crime than it is up here, this is still more effective. This still has a bigger influence on the pKa because of the resonance. And by the way, notice that the nitro group is a very sort of strange group, right? The nitro group, nitrogen can only have 4 bonds to it. So naturally, the way the nitro group lives in the world is to have a positive charge on the nitrogen and a negative charge on the oxygen. That's just the way it is, because the nitro group has this weird sort of structure, and that's one of the reasons why it's so incredibly polar, because it does have that separation of charge going on there. Then we have our proximity effects, which can do with things like steric effects and intermolecular hydrogen bonding. So, for example, here's a benzoic acid with a hydroxyl group that's para, so they're far away from each other. So the first pKa, you take off this proton, pKa 4.48, and then if you want to take off the second proton, you can do that, and the pKa is 9.32. But if you move that hydroxyl group over here to the ortho position, now the first pKa is quite easy. It's much easier to take off the first proton. It goes from 4.48 all the way down to 2.97. Very easy to lose this proton because this proton is coming and kicking it out. It's saying, get lost, buddy. I want your oxygen. So this proton gets kicked out really easily, but then this proton is now being held through this intermolecular hydrogen bond. It forms this six-membered ring. So this proton is now being held onto very tightly by two oxygens, no longer just by one. So its pKa is now much, much higher. pKa here was 9.32, but now it's all the way up to 13.4. So it's gone up by 4 orders of magnitude because of that intermolecular hydrogen bonding. And now I'm not a good enough organic chemist to just look at this and say, ooh, I can imagine intermolecular hydrogen bonding going on. I would not know that without having, like really thinking about it and drawing out the structures. So these are really tricky effects. You can't always predict how they're going to behave. And then here's an example of some steric effects. So here's an aniline with these two methyl groups on it. Here it is in its neutral state. If it picks up a proton here, these methyl groups can rotate. There's rotation about this bond right here. And so when it's in this form, you can imagine the ring is in the plane of the board, and the lone pair electrons are sticking out of the board at you and behind the board. And so they are resonating with the ring. In order to do that, these methyl groups have to be in the same plane as the ring. And that's fine. We can do that because these methyl groups are pretty small. But if you make them a little bit bigger and make them ethyl groups, now it becomes much more difficult. They're sterically hindering the rotation around this bond right here. See if I can draw a little arrow. There we go. Oh, not so bad. They're sterically hindering the rotation around that bond because for them to be in the same plane with the ring is creating some steric hindrance because these are just big and they get in the way. And as a result, this thing rotates so that the lone pair electrons are out of plane. They're not resonating with the ring anymore because they don't have a right geometry. And consequently, the pKa goes up by a whole order of magnitude. So steric effects can have a big influence on the pKa of these compounds. That's a good place to take a break.